Hello everyone, now we will discuss on the topic sampling and characterization part 3. In this class we will discuss sampling of solid waste and soil, characterization of solid waste, that physical and chemical characteristics of solid waste and the methods for this characterization like say proximate and ultimate analysis, fusing point of ash, lignocellulosic composition, leaching properties and energy content. These are the chemical characteristics, and first we will see how to sample the solid waste or soil samples. So, solid waste sampling may often involve direct sampling either at the source or from a vehicle load. So, vehicle load sampling is often carried out by sampling the waste received at waste transfer station, waste treatment facilities, that is waste incinerators and landfill sites. Important sampling methods are random, systematic, stratified and quartering. To ensure uniform coverage of the geographical area under study, stratification sampling is often applied. This involves dividing the study area into non-overlapping sub areas with similar characteristics. You see, this is say we are going for random sampling. So, this is our collection area or study area. So, for any point randomly we can get the samples, and here zigzag. So, in that way randomly we are taking also. So, this is zigzag nature, and stratified sampling means, so same area we are interested to get more accurate result or sample. So, we can divide into 4 equal non overlapping area, and from each area we can collect equal number of samples, maybe randomly, and if we want to make more accurate then we can go for systematic sampling. So, equal distance, equal direction like this. So, that way the sampling methods are followed. So, random sampling, stratified sampling and systematic sampling methods are evaluated for precision and efficiency in soil analysis. The procedure for obtaining soil samples varies according to the purpose of sampling, and for random or zigzag sampling each soil core is selected separately, randomly and independently with a simple random system. Suitable for uniform fields, samples are collected in a zigzag or random pattern across the field. And stratified sampling, a stratified random sample is taken from a field that has been divided into several sub units or quadrants from which random samples are obtained. And systematic sampling, the systematic sample is a further progression to ensure complete field coverage, similar to the change from the simple random to the stratified random. This method takes samples at regularly spaced intervals in all directions. Then how we will collect the samples? So, here scrape away surface litter. So, surface litter is scraped away and obtain uniform thick slice of soil from the surface to the plough depth from each place. So, where we are collecting, so every place we will be following the same method, and say here a V shape cut to a depth of 15 centimeter, a V shape cut 15 centimeter depth up to this. Then what we will do in the sampling spot, using the spade to remove 1 to 2 centimeter slice of soil. So, one side we will be taking the soil, so 1 to 2 centimeter slice of soil. So, this is the soil sampling a typical method. The sample may be collected on the spade's blade and put in a clean bucket, and the samples to be mixed thoroughly, and foreign materials like roots, stones, pebbles and gravel to be removed, because we will be collecting number of samples from different places, then we will mix it. And quartering, another method is there, that is mostly used for solid waste sampling. So, solid waste is divided into 4 sections after cutting large pieces and mixing, and 2 diagonal sections are again mixed. These operations shown in figure below are done several times. So, say we have made 4 quarter A, B, C, D. So, A, B, C, D. So, this diagonal C, D and A, B will be mixed, again we will follow the same process, again will be mixed, likewise number of times we will do and we will get the uniform sample that way. So, finally, samples are collected in a clean cloth or polyethylene bag. For analysis, the soil material is sieved through a 2 millimeter sieve, and to determine the organic matter, it is desirable to grind a representative subsample and sieve it through a 0.2 millimeter sieve. So, these are the methods which are used for the sampling of solid waste and soil. Now, after the collection of samples, we have to analyze, we have to characterize these. So, for physical property assessment or physical characterization, so specific weight or density we have seen, and then particle size and size distribution, permeability or hydraulic conductivity and moisture content are important, and we will discuss how to measure this. So, specific weight or density is defined as the weight of material per unit volume, we know it very well, and there are 3 densities associated with the powders. One is absolute density or true or skeletal density, another is envelope density or apparent density, and third one is bulk density. So, the absolute density, it excludes the volumes of pores and of the interparticle spaces of the powder material, and envelope density includes the pore volume, but excludes interparticle spaces, and bulk density includes both pore volume and their particle spaces. Its value changes with the degree of compaction. For example, here you see loose MSW, no processing or compaction, its density is 90 to 150 kg per meter cube, but if we make the compaction, then in compaction track it is 355 to 530 kg per meter cube. So, the density increases. So, measurement of density is done by true density and tap density analyzer, normally by employing Archimedes principle of fluid and fluid displacement and the technique of gas expansion. Now, particle size distribution is very important, because you want to use these waste materials for different applications for recycling, then the performance of the process will be influenced by the particle size of this material. So, this can be done, and for this particle size analysis can be done by sieve analysis. Trommels are using particle size analyzer depending upon the size of the particles. So, bigger the particles we can go for the trommels, intermediate we can go for sieve analysis, or smaller, and then finer particles we can go for the particle size analyzer. And when we go for sieve analysis, then there are basically 2 major ways to represent the experimental data, like say average size and mass fractions if we measure. So, that we can express in this way. So, x axis is diameter and y axis is cumulative mass fraction. So, we can put cumulative mass fraction, so that way we can get, or simply we can put x 1, x 2, x 3, x 4, x 5 like this. So, like fractions we are having. So, this x 1, x 2, x 3, x 4 we can put it here, or as a cumulative we can put it here. Now, hydraulic conductivity. So, hydraulic conductivity, it is a measure of the ability of porous media to conduct liquid. Although testing of hydraulic conductivity is simple in theory, movement of water through a medium is very complex. Factors affecting hydraulic conductivity are particle size, fabric, degree of saturation, pore geometry and properties of the test fluid. However, it is difficult to characterize MSW samples based on these factors due to heterogeneity of MSW. Municipal solid waste is heterogeneous and that is a major problem for this also. Next we will see the moisture content measurement. The moisture in a sample is expressed as percentage of the weight of the MSW material. It is determined by using hot air oven, where the material is heated at 105 degree centigrade till constant weight is achieved. Like say this type of oven is used and then it is heated at 105 degree centigrade until a constant weight is achieved, and it is calculated by the following formula: the percentage moisture is equal to loss in weight divided by weight of material taken into 100, basically mass of. Now, we are going to discuss about the characterization of chemical properties or the analysis of chemical properties, like say proximate analysis, which includes the moisture, volatile matter, ash content and fixed carbon in the sample. Ultimate analysis, that gives us CHNS, carbon, hydrogen, nitrogen, sulfur and oxygen, and fusing point of ash, lignocellulosic composition and leaching properties applicable to hazardous waste fractions in MSW waste, and then energy content or heating value, that we are going to discuss one by one. So, proximate analysis. So, moisture determination already we have discussed how to do it. So, that is loss in weight of sample due to drying at 105 degree centigrade for 24 hour, and then for volatile matter. So, this is the loss in weight of moisture free sample ignited in muffle furnace at 950 degree centigrade for 7 minutes in the absence of oxygen in a closed crucible. That means, after the removal of the moisture, we will be taking the sample and then heat it at 950 degree centigrade for 7 minutes in absence of oxygen, then the vapors will be goes off, that is the volatile materials will go off, and then we will measure how much mass is remaining. So, that we will calculate the percentage of the volatile matter. And for the determination of ash content, so weight of residue left after combustion of dry sample in muffle furnace at 750 degree centigrade for half an hour in the presence of oxygen in an open crucible. So, what we are getting, the residue which is remaining after the volatile matter determination, we can heat it at 750 degree centigrade in presence of oxygen. So, then also its mass will be reduced and some amount will be residual. So, that will be the basically ash content, and fixed carbon we will be measuring by getting the difference. So, 100 minus moisture content minus volatile matter content minus ash content. Now, some example is given here, different types of waste materials, say mixed food, mixed paper, mixed plastics, yard waste and residual MSW. So, moisture content, a typical moisture content values is shown here, typical volatiles are given here, fixed carbon content are also given typically, ash content also are provided. So, these are some typical example of different types of waste materials. Now, ultimate analysis. So, ultimate analysis or elemental analysis or CHNS analysis is determined by the CHNS analyzer. So, the principle of CHNS analyzer depends on the tendency that all atoms prefer to be in their oxidation states. In presence of pure oxygen and high temperatures of 90 degree centigrade, all carbon easily burn to become carbon dioxide, all hydrogen burn to become H2O and all nitrogen becomes N2 gas or various nitric oxides. So, nitrogen is converted to NOx. For analysis, product gas mixture flows through a silica tube packed with copper granules. This zone held at about 550 degree centigrade, remaining oxygen is bound and nitric or nitrous oxides are reduced. The leaving gas stream includes the analytically important species CO2, H2O, N2. Eventually, SO2 is absorbed at appropriate traps. So, basic concept is that we need to apply excess heat and then to convert it into the oxides of the different elements that like CO2, H2O, SO2, N2, etc., and then reduction of NOx to nitrogen again and separate the SO2 and analyze it. So, sample and carrier gas combustion will take place, then reduction for NOx to nitrogen, and then it will be mixing and then separation. So, after separation we will get the detection. So, just like gas chromatography which we have discussed. So, one gas chromatography is used or gas analyzer also termed it is. So, on the same principle of gas chromatography. So, in this case depending upon the retention time, different oxides like say CO2, H2O, SO2 and N2 which is reduced, the NOx which is reduced, they will be coming out from the column, capillary column at different time intervals, and as NOx is reduced to nitrogen prior to its analysis. So, nitrogen will have no interactions, it is inert gas. So, it will very quickly coming out, it will come out very fast and we will get the peak of nitrogen at the first step, and then carbon dioxide will come out, and then H2O will come out, and then SO2 will come out, and we will be able to identify these gas components, and also we will be able to determine the concentration of these gas components by calibration with some known samples. So, high purity helium is used as carrier gas. Finally, the gas mixture is brought to a defined pressure of volume state and is passed to a gas chromatographic system. Separation of the pieces is done by so called zone chromatography. In this technique, a staircase type signal is found. So, step height is proportional to the substance amount in the mixture, and some typical example you see say mixed food, mixed paper, mixed plastic, yard waste and refuse derived fuel. So, carbon, hydrogen, oxygen, nitrogen, sulfur, NH content are provided here. Now, we will discuss fusing point of ash. So, fusing point of ash is the temperature at which the ash resulting from the burning of waste forms a solid or clinker by fusion and agglomeration. The typical fusing temperature is 1100 to 1200 degree centigrade. Experimentally, it can be determined by fusing by using a furnace. So, there are 4 types of ash melting temperature. If we apply heat to the ash, then initially after certain temperature it will shrinkage, and that is shrinkage temperature, then it will deform. So, that is deformation temperature. Further heating or more temperature, so we can get a hemispherical form, that is hemisphere temperature, and further heating, and then we can see the flow of the ash. So, that is called flow temperature. So, these different types of temperatures or phenomena we can see by the application of heat on the ash, and ash melting temperature can be predicted from chemical composition of biomass ash. There is a need to know the composition of SiO2, CaO, K2O, MgO and Al2O3 in biomass ash. There are some empirical relationship that can be used to determine the ash fusion temperature of the ash. Now, we will discuss analysis of cellulose, hemicellulose, lignin and extractives in the lignocellulosic biomass. So, for the determination of this, at first we determine the extractives, and basically some solvent is used, that is benzene and ethanol mixture, and the sample is taken into this, and then after vigorous mixing with volume ratio of 2:1 and a fixed temperature for 3 hours. After leaching, the residue is dried in hot air oven at 105 degree centigrade to a constant weight. Then the dried sample is cooled in a desiccator and weighted, that is M1 we are getting. So, the mass percent extractive is W1, that is MO minus M1 by MO into 100. So, when we are using the solvent, the volatiles will come into the solvent phase, then we are vaporizing the solvent, and then the remaining will be the mass, and what mass we are losing, we are losing. So, that will be the mass loss due to the volatile matters, and that MO minus M1 by M into 100 will be the percentage of the volatiles. Then for the determination of hemicellulose, so after the determination of extractives, the remaining material we will treating or we will react it with NaOE solution, and that is 150 ml NaOE solution 20 gram per liter, that is, and then the mixture is boiled with 3.5 hour with recycled distilled water. After that, the residue is washed with distilled water till no sodium ion present in wash liquor and dried it to a constant weight. The dried sample is cooled in a desiccator and weighted, that is M2 gram. The mass percent of hemicellulose W2, that is equal to M1 minus M2 by MO into 100. So, then we will see the lignin concentration, and for that about 1 gram of residue after extractive analysis is dried to a constant weight. Then the sample is cooled and weighted, that is M3 gram. After that the sample is mixed with 30 ml sulfuric acid of 72% concentration and kept at 8 to 15 degree centigrade for 24 hours. The mixture is diluted with 300 ml of distilled water and boiled for 1 hour with recycled distilled water. After cooling and filtration, the residue is washed with distilled water till no sulphate ion present in liquor, which is detected by 10% barium chloride solution. Then the residue is dried to a constant weight and cooled in a desiccator and weighted M4 gram. The mass percent of lignin W3 is M4 into 1 minus W1 by M3 into 100. So, we can calculate the percentage of cellulose by difference, that is 100 minus W1 plus W2 plus W3, when percentage of cellulose is your W4. So, that can be calculated like this. So, W1, W2, W3. So, extractive, hemicellulose and lignin. Now, we will discuss about the leaching test, that is TCLP, toxicity characteristic leaching protocol or TCLP. This mimics conditions found in landfills when groundwater percolates through buried materials. So, we will be generating some synthetic solution and then we will be putting the waste material in it, and we will be providing some shaking arrangement and for certain time, so that the leaching will take place and we will see the concentration of the pollutants in the solvent. So, the TCLP is designed to determine the mobility of both organic and inorganic analytes present in liquid, solid and multiphagic waste. So, different heavy metals as shown here, say 8 heavy metals, organic solvents, different organic solvents as shown here, arsenic, barium, cadmium, chromium, lead, mercury, selenium, silver, here benzene, carbon tetrachloride, 2,4 dinitro, toluene, hexachloro, ethane, methyl ethyl ketone, nitrobenzene, tetrachloroethylene, trichloroethylene, pyridine, chloroform, vinyl chloride, cresols. These are the different pesticides as mentioned here. Those can also be tested for leaching purpose, and for this we have two types of apparatus and two types of solvent also. So, one apparatus is zero head space extraction vessel. So, zero head space, we are not providing any head space, particularly when we are interested to get the extraction properties or the leaching properties of the components which are vaporizing in nature, which can be easily vaporized. In that case, we will be using this type of setup. So, this device is for use only when the waste is being tested for the mobility of volatile analytes like acetone, benzene, N-butyl alcohol, carbon disulfide, carbon tetrachloride, carbobenzene, chloroform, chlorobenzene, chloroform, etc. And bottle extraction vessel, in this case we do not have any head space. Okay. When the waste is being, in this case we have head space, when the waste is being evaluated using the non volatile extraction, a jar with significant capacity to hold the sample and the extraction fluid is needed, head space is allowed in this vessel. So, this is the photographs. Then we will be giving some rotation, it may be horizontally or maybe shaft may be vertically. So, that can be done. And as I mentioned, so two types of solvent we can get, that is with relatively higher pH and relatively lower pH. So, extraction fluid 1, that is pH is 4.93 plus 0.05 and in this case 2.88 plus 0.05. So, lower pH. So, in this case pH increased by addition of NaOH and basically the glacial acetic acid is used to get this 2.88 pH. So, 5.7 ml glacial acetic acid is added with reagent water to a volume of 1 liter, when correctly prepared the pH of this fluid is 2.88 plus 0.05 and in this case 5.7 ml glacial acetic acid is added to 500 ml of reagent water added with 64.3 ml of 1N NaOH and diluted to a volume of 1 liter. When correctly prepared, the pH of this fluid becomes 4.93 plus 0.05. All reagents used will be certainly analytical grade. Now, we will discuss heating value. So, heating value, when we are talking about the waste materials. So, if we combust this waste material, then it will be converted to flue gas. So, flue gas will be having high temperature. So, when we will use this flue gas to generate steam. So, then the heat available in the flue gas will be converted to the steam, and the heating value is defined is the amount of heat released by the combustion of unit mass of the material. So, by knowing the amount of heat released and how much material has been used, we can calculate the heating value. So, heating value of a substance is the amount of heat released during the combustion of a specified amount of it. It is measured in units of energy per unit of the substance, usually mass, such as kilojoule per kg, kilojoule per mole, kilocalorie per kg, BTU per pound, and heating value unit conversion is also there. So, that kilocalorie per kg to megajoule per kg. So, in that case we have to use this conversion factor, and we know there is two types of heating value, one is high heating value and another is low heating value, and high heating value is also called gross heating value and low heating value is also called net heating value. So, how can we explain these and how can we determine? How can we explain these? Say we have a waste sample, we are combusting it here, then flue gas is coming out. So, flue gas we are using some water, so it is converted to steam. So, this is our waste, this is your combustor. Okay. So, then this is our flue gas, high temperature flue gas, it is coming, water is converted to steam, and then this is going as flue gas to environment, atmosphere or environment. Okay. Now, if we have certain amount of material, then heat is generated here then after changing the heat, transferring the heat, if the flue gas temperature here it is come down to ambient temperature, which we had here at the start of the reaction, the same temperature, then we can assume how much heat was available here, that is completely recovered in this step. But if this flue gas is getting into the environment at higher temperature, so this is your T1 and this is T2. So, T2 is your ambient temperature Ta, and if T1 is greater than Ta, in that case some amount of energy is already associated with this flue gas which is coming into the environment, and we are not able to take that heat out from it for our useful application. Okay. So, in this case, when we are able to extract the energy available in the flue gas which were generated during the combustion of the materials, then that heating value per 1 unit of this waste material will be higher than this value. So, this is called high heating value. So, high heating value is determined by bringing all the products of the combustion back to the original pre-combustion temperature, and in particular condensing any vapor produced. Such measurements often use a standard temperature of 15 degree centigrade, that we are talking about, that this is our standard how much temperature was there. And lower heating value is determined by subtracting the heat of vaporization of the water vapor from the higher heating value. This treats H2O formed as a vapor. The energy required to vaporize the water therefore, is not released as heat. So, in this case this temperature is higher, say 100 degree centigrade. So, if this temperature is 500 degree centigrade or 600 degree centigrade, here I am getting say 150 degree centigrade. So, this amount of we are losing some amount of energy here, and water which was produced here due to the combustion, that is available in steam form. But here if it is condensed, its temperature is ambient temperature, that water will be condensed. So, that will be the basically the difference in this high heating value and low heating value. A common method of relating HHV to LHV is HHV, high heating value, is equal to low heating value plus HV into NH2O out by N, that fuel. So, HV is the heat of vaporization of water, and NH2O out is the moles of water vaporized, and N is the fuel, that is equal to number of moles of fuel combusted. So, how many moles of fuel is combusted and how many moles of water is produced by the combustion of this 1 mole of fuel, multiply it with the latent heat of vaporization of water, then we add it with the LHV, that will be HHV, because we are assuming that the moisture which was generated, that is in steam form, it is not condensed. So, that energy is additional here. So, we are not able to take it out. So, if we add with this energy with this LHV, so we will get the HHV. So, up to this in this class, thank you very much for your patience.